Welcome to the Planet Earth podcast. I'm Richard Hollingham in a dark, low, damp, slightly sinister tunnel. And this tunnel once connected the courthouse in Norwich with the prison. Today, I hope it leads to the archaeology study room. I'm on my way to find out about Roman recycling. Also this week, an update on Europe's gravity space mission and the fossils helping to reveal the colour of dinosaurs.
The bones are a kind of cream colour and almost chalky in appearance, and these are the wing bones here. Here's the backbone and the ribs there. And I think, yes, here's the head kind of bent back, almost over the top of the thing.
Well, I've made it along the tunnel to the archaeology study room, and, well, it's pretty much got the history of the world in here. There's some chains here, you can hear clunking in some paper. Down here there's some handcuffs, there's some pottery, glass, some other fragments, I can't quite tell what they are, pictures on the wall of an Anglo-Saxon brooch, you've got knights, and table in the centre is a box of glass which I'm told I must not touch. I'm joined by Harriet Foster from the Norfolk Museums and Archaeology Service and Caroline Jackson from the University of Sheffield. Now, you've been working on Roman glass recycling. Before we get on to that, Harriet, tell me what's on the table in front of us. Very delicate looking glass, although, easily recognisable. Got a vase, some cups and a bottle here in shades of green.
Yes, what we've got are 6 vessels, 3 drinking vessels and 3 other vessels which are closed forms. So you're right, there's 2 jugs and a bottle, and they're all late 4th century.
Now we've got here a modern glass, which I am allowed to touch. Actually, you look at this, mass-produced modern glass, and you compare it with these from almost 2,000 years ago, Caroline.
That's right.
These glasses could almost be mass-produced because they're 3 glasses, pretty much identical, and you can imagine those in a box at a supermarket or something.
Well, that's right. They actually were mass-produced in a way. Glass production, certainly by the 4th century, was something which was prolific. Glass is found in most archaeological contexts. It's all blown glass. This is something which came in certainly in the Roman period. The Romans are said to have developed and invented glass blowing, something that perhaps wasn't around in earlier periods. So to produce the glass by blowing is very rapid, it's very quick, and it's a very easy technique once you've mastered it. So you can produce many, many vessels from a small amount of glass, and this is why these have such thin walls as well, because they're blown.
How do you know they recycled the glass?
We've known for a long time that the Romans recycled glass. We've got evidence from a late 1st century AD source that talks about broken glass in Rome being collected up in exchange for items of small worth. And there's archaeological evidence for glass recycling, so we find the equivalent of bottle banks.
So what did you do then?
We took a lot of material from about 20 sites in Britain and analysed them chemically to see if we could see anything within the compositions which might give us an indication that recycling was taking place. And the results of that were quite surprising.
Mm-hmm. They were surprising because of the amount of recycling that we found that was going on. A significant proportion of the assemblage that we looked at, which was over 500 samples, suggested to us that the glass was being recycled in quite large amounts. And that was interesting because it throws up more questions about, well, what does that mean about the supply of glass to the province at the time? Was glass being recycled because there weren't fresh supplies available, or is it something else?
Have you got any ideas why this might have been going on?
By the late 3rd and 4th century, the Roman Empire is starting to change. The large industrial complexes that you see are starting to decline. There are political events going on which are making the empire start to certainly not, it's not expanding anymore, and it's perhaps starting to contract. And if you think about the withdrawal in the 4th, 5th century out of Britain. It's all part of the same thing, and I think trade is starting to contract. Now, we don't know exactly what was happening with supplies of glass because we don't have any archaeological evidence at this point that is published where we know glass was being produced. So we can't say this factory stopped and maybe that factory started, but we can say that it looks as though that supply of raw glass is starting to decline because there is a greater proportion of recycled glass that you can see in the chemical fingerprint. So the recycling is showing a greater mix of glasses. We've got elements in there which can only come from mixing, that can't have come from the raw materials. So we know that a very large proportion of the glass is being recycled. And that's not just for the common forms and the common colours. Even the sort of more high-status, colourless glass, which is always thought of as something which is reserved for perhaps more specialised vessels, even that is showing evidence of large-scale recycling. So it's going on throughout the glass industry.
OK, so you're learning about the glass, but you can also, by using the glass, tell a lot about how the society was changing as well.
Well, that's archaeology. That's what we do. The glass is a really interesting material, but it's only interesting in what it tells us about the people who were making it and consuming it. In the same way as we look at any archaeological material, it's there for a purpose. It's there to tell us about people, the individual and society.
Caroline and Harriet, thank you both very much. Now, here's a question. What colour are dinosaurs? How do we know they weren't pink with blue stripes or purple with orange spots? It's a question that's bothered paleontologists since the creatures were first discovered. But now the first evidence is emerging of the true colours of dinosaurs. Evidence which should help scientists understand the origin of birds. Professor of Paleontology at the University of Bristol, Mike Benton, is a member of a UK and Chinese team working on dinosaur and bird fossils found in China. He showed me the fossil of an 125-million-year-old bird.
So we have some specimens here.
So you're opening a locked cabinet and pulling out a drawer here. Now this
is an astonishing
this sample
little
fits in
specimen.
about the palm of your
yes,
hand.
palm of my hand, and this is a complete little bird. So
it does look like a crushed skeleton of a bird.
Yes, and you can see that the bones are a kind of cream colour and almost chalky in appearance, and these are the wing bones here. Here's the backbone and the ribs there. And I think, yes, here's the head kind of bent back, almost over the top of the thing. And around it is a halo of fluffy, bluey-grey material, which are traces of the feathers. And you can see at the edges they become wispy. And so we were then focusing on this dark grey material, which is obviously remnants of soft tissue.
It is coloured. There are different shades of brown and grey. Can you say that they were the colours of the feathers then?
No, I think that's been the question so far. There are many fossil birds and now many fossil dinosaurs with rather obvious feathers around the edge. And nobody can deny that they're feathers because in many cases they have the detail of a wing feather with a quill up the middle and the branching barbs at the side. Others, like these ones here, are the sort of wispy down feathers, as we would call them, that cover the whole body area and the base of the wings, and are there mainly for insulation. But as you look at them, the differences in tone, the different shades of grey, you would be foolish to try and interpret those as original colour.
So you've got some of the samples that you put under the electron microscope. We can hear this electron microscope buzzing away behind us. If we look at the screen here, you've got one of the images when you're zooming in to sort of micron level,
so this
level
here.
Here.
Is 2 microns.
And it's almost like a series of little rugby balls all jammed together.
Yes, they're sort of arranged higgledy-piggledy. You can't see particular rows. So these little structures, judging by their shape and size, we're pretty certain that these are what are called melanosomes. Melanosomes in feathers of modern birds are introduced at the very early embryonic stage of the feather, as it sprouts from the skin. And they come from the skin itself. So melanin is a well-known chemical that occurs throughout almost all organisms. Mostly it gives a black colour, And in the case of birds, it is produced within the skin, and then it is packaged in a particular way before it goes into the feather, because the keratin that makes the feather is rather like a plastic, or it's quite hard, solid material, and in order to get the chemical in, it has to be packaged into these organelles.
So a particular shape gives you a particular colour. Is that what you're looking for?
This is what we're looking for, and it is a remarkable fact that across all modern birds and across, indeed, all modern mammals, there are two main kinds of melanosomes, and there are numerous others in between, but the two main end members are a sausage-shaped melanosome that's about 1 micron in length, and at the other end is a spherical melanosome that's about half a micron across, or just slightly less. And these two end members always correspond to black and ginger. So the long sausage-shaped one is black to dark brown and is called a eumelanosome, and the spherical one at the other end is a ginger colour and is called a pheomelanosome.
So let's zoom back out from these samples you've got at the micron level under the electron microscope to this dinosaur bird. What does it look like?
So we looked at a number of different dinosaur specimens from China, but the one we were particularly keen to study in detail is called Sinosauropteryx, and it was a small turkey-sized animal with a long, thin tail. But the reason we chose it was because it has the most primitive feather-like structures, and we thought if we can not only determine the colour but also determine whether these are feathers or not, then we're doing something important in terms of the evolution of the group. So we had two things to do, and we looked at some of the dark-coloured ones and found that they were full of pheomelanosomes, the ginger-giving melanosomes. So we believe this shows two things. First of all, that these simple bristle-like filaments actually are some kind of a feather, and that's important. And secondly, they happen to be ginger. So we can reconstruct this dinosaur at least with a ginger and white striped tail, like a barber's pole.
Now, this isn't just about getting the colour of dinosaurs right in textbooks or in paintings or whatever. There are implications for evolution here.
We were particularly interested in understanding why birds are so successful. There's a simple question. 10,000 species today. Their evolutionary tree can track back to Archaeopteryx in the Upper Jurassic 150 million years ago. It's very important in terms of us understanding how a reptilian scale, as would have been present in dinosaurs and as we see in lizards and crocodiles today, how a reptilian scale can become a feather, because of course feathers must be crucial to the success of birds, and therefore to tease that apart is quite important.
Mike Benton from the University of Bristol, and you can see a picture of the dinosaur on the Planet Earth online website. Put the words colour and dinosaur into the search box, but don't forget colour is spelt the British, the proper way, with a U. Also on the website you'll find research news on how warm summers can slow down the advance of glaciers, shellfish hearing, and the advantages for conservation of promiscuity. Over the past couple of years on the Planet Earth podcast, we've been following the progress of three important European space missions. Cryosat, investigating the Earth's ice coverage, SMOS, assessing soil moisture and ocean salinity, and GOCE, which is a somewhat tortured acronym for Gravity Field and Steady State Ocean Circulation Explorer. Well, later this month, the European Space Agency is releasing a fresh batch of data from the GOCE satellite to an eagerly awaiting scientific community. Sue Nelson has the latest.
Launched in March 2009, GOCE's aim is to help scientists understand how ocean circulation moves energy around our planet. The latest information from the satellite adds up to 6 months' worth of data, with the first 3 months already producing results. Helen Snaith from the National Oceanography Centre, Southampton.
They've been generating new gravity fields, better estimations of what the gravity field looks like, and the oceanographers have started to use those gravity fields to determine ocean currents.
And in December at the American Geophysical Union, a map was produced that has never been seen before, and that was purely from GOCE data.
From GOCE data, actually in combination with satellite altimeter data, because we need the two to get the ocean currents. We have a map of the ocean currents purely from satellite data that shows a lot more detail than we've managed to see from this kind of map before. We now have the kind of detail in where the ocean currents are that we've only been able to get in a few locations using in situ measurements before.
The map, produced by the University of Newcastle and available on the Planet Earth online website, portrays the world's landmasses in black silhouette on top of rainbow-coloured seas and oceans. On these oceans are black lines resembling the pressure bars on a weather map.
They're exactly like the pressure lines that you see on a weather map. They're actually the height of the sea surface. They represent lines where the currents will run along these black lines in the same way that the wind will blow round the pressure lines on a weather map. And on this map, the blue areas are where the sea surface height is fairly low, and the red areas are where it's quite high. And where the black lines are very close together, that's where we get very strong ocean currents.
One such collection of close black lines off Florida turns eastwards across the Atlantic and clearly represents the Gulf Stream. And the map shows the currents and the circulation that helps to control our climate in Europe. But it's the new data that is causing the most interest.
There are some areas of the ocean where this map is particularly important. In the Gulf Stream, we take quite a lot of in situ measurements with ships and with buoys because they're very important to us. But in areas like the middle of the Pacific, which is a massive area, we simply can't hope to get the in situ measurements. And we can start to see in this map far more detail of how the ocean currents, how the circulation is affected by islands. This is the kind of information that we're really trying to capture using Gautier, because that's the small scale of features that we haven't been able to get from other gravity field measurements on a global scale.
Now, the colour scale beneath it goes from minus 1.4 metres to plus 1.4 metres, so just under a 3 metre difference there. And what does this difference of 3 metres stand for?
This is actually the change in the sea surface height that is caused purely by ocean currents. Where you have an ocean current, you will have a high sea surface height on one side and a low sea surface height on the other. So this is a physical difference in the height of the sea surface.
And what's the difference between that, this sort of plus or minus 1.4 metres, and the effect of gravity on the sea surface?
This change in height from the ocean currents effectively sits on top of the shape of the sea surface that's controlled by gravity. And that shape has height differences from about minus 100 metres to plus 100 metres. So much, much bigger.
I mean, that I find that almost hard to believe, because when you think of the sea, you think of it as being flat, consistent, not something that could vary. Its surface could vary by hundreds of metres.
Yep, that's right. When you look at the surface of the ocean, the surface of the sea, it looks flat. The changes aren't on the kind of scale that you can see by looking at and by standing out on a cliff and looking at the surface of the ocean. But the changes, for example, from the middle of the South Pacific to just north of Australia, so over several thousand kilometres, the height of the ocean surface changes by 150 to 200 metres. The gravity field controls the shape of the sea surface to a huge extent.
Helen Snaith from the National Oceanography Centre ending Sue Nelson's report on the Gautier satellite. And next time, Sue will be updating us on SMOS.
One is charged with the Roman lines.
I've come through now to the Castle Museum in Norwich, into the Roman Gallery, where Boadicea is taking on the Romans behind me. And in front of me, a series of shelves with some more Roman glass. And Caroline Jackson from the University of Sheffield is still with me. Now, it's not the intricate glass here that gets you excited. It's not the beautiful blue at the back. It's the chunky greenish glass sitting on the shelf at the front.
That's right. These are utilitarian bottles. They're mass-produced, they're blown into moulds, and they're important because they are used for and consumed for what they contain, not because of the glass. So it tells us a little bit about what was moving about in the Roman Empire. These glasses were, like milk bottles were up to fairly recently, reused. So the contents were consumed, the glasses were washed and then refilled and then retransported en masse. They're square, so they fit together very nicely. You can move them by land and you can move them by sea.
The idea really is that nothing much has changed.
Not really, no. We've been doing exactly the same up to fairly recently. And if you think about what we're doing now, people are being encouraged to reuse glass vessels. And that's what's going on in the Roman period.
Well, Caroline, thank you very much. And that's the Planet Earth podcast. All our past editions are available on the Planet Earth online website, and you can get in touch with us via the Planet Earth online Facebook page, where you'll also find pictures of the glass we've been talking about today and videos. Next time, Sue's off to see a big dish in Hampshire. I'm Richard Hollingham. Thanks for listening.